Solid, a term hard to avoid if you've worked in software. It's an acronym for 5 principles in programming that strive to result in better code. These principles are single responsibility principle, open-closed principle, Liskov substitution principle, interface segregation principle, and dependency inversion principle. Single responsibility principle is about designing modules or classes in a way that they only have one reason to change. Reason here generally means an area of responsibility. That is, one class should only have one responsibility. Let's take a look at a C# example. Suppose we have a simple program that can read a list of people from a CSV file and print them to the console. Let's start with the naive implementation of writing it all in main. This code would break the single responsibility principle, as the program class now has many responsibilities. It handles input arguments, reads the CSV file, formats output, and writes output. If we wanted to make changes to any of these responsibilities, we would always have to modify the program class. So let's split this into 3 classes. Now we have split input reading, formatting, and reading the CSV file into their own classes. Output writing can be considered handled by console write line. So this code is now following SRP, at least an interpretation of it. Open-close principle means that a module should be open for extension but closed for modification. What this means is the external interface of a module should expand over time, supporting different variations of methods rather than changing the existing methods. Changing the existing methods will break compatibility with dependencies, which triggers extra work for you as a developer and can be quite hazardous if you are not in control or aware of all the users of the module. In our example, let's say we want to extend the person CSV reader to support other delimiters for reading the CSV file rather than just the default. Here we have added a new method that takes the additional delimiter parameter, leaving the signature of the old method intact. This maintains compatibility with our existing usage in the program class, while allowing us to support this new use case of custom delimiter. The Liskov substitution principle sounds fancy, but it's really simple. When a base class is referenced, all objects deriving from that base class should be usable with that reference. A base class can also be an interface in this case. What this means in practice is that you should avoid situations where a derived class overrides methods or properties of a base class and then does something like raise a not implemented exception. The interface of the base class should be assumed usable no matter what the subclass is. Let's say we changed our example to support reading persons from a JSON file in addition to a CSV file. This example would violate the Liskov substitution principle. The interface is exposing the read method with delimiter parameter, but our JSON implementation does not support it and raises an exception. The delimiter is an implementation detail of CSV reader, so we can remove it from the common interface and provide it into the CSV reader constructor instead. Now the Liskov substitution principle is being followed. Next is the interface segregation principle. This principle is about keeping interfaces logically separate, so that if some code is dependent on an interface, it does not have to be dependent on another logically different interface. Say we want to expand our formatter to support a new concept, books. A book has an ISBN and a name, and we need a formatter to turn it into a displayed string. Let's expand the person formatter to support this. We have now violated the interface segregation principle. Our program only requires formatting of people, but because the formatting of people and books are coupled into the same interface, the program is also coupled into the book formatting, even though it does not need it. We can fix this by creating 2 interfaces, one for people and one for books. Now these interfaces can be implemented by the same class, but that class can be cast to either of the 2 different interfaces, making them decoupled. Lastly, we have the dependency inversion principle. Dependency inversion is about separating implementation of modules from their interfaces and ensuring that modules only depend on the interfaces of other modules and not concrete implementation classes. We can demonstrate this principle by creating a write-to-console class that will do what the program currently does. As you can see, this class does not need to depend on any concrete implementations. It only depends on interfaces. And those are the solid principles. These are often taught in the context of object-oriented programming, like I just did with C# examples. But the principles can be applied without objects as well. Notice how I use the term module. Modules are a larger concept than just classes in OOP. A module can be a collection of multiple classes, functions, and data structures. You don't necessarily need an interface between every class. It is okay to have classes directly depending on each other, for example if they are all in the same module. In a real application, I would consider the entire previous example as a single module, but for demonstration purposes I split it into multiple modules. In the end, code-based design is about minimizing complexity. The software is intended to solve a certain problem, and its implementation should not be any more complex than what the problem requires. Any extra complexity is a cost with no benefit. One of the biggest causes of complexity in software is dependencies. Reducing dependencies reduces complexity, and that's where the solid principles can help. Try to apply the principles in your project so you can get a more solid grasp on them. Thanks for watching this video. Please like and subscribe if you want to see more videos related to the software development. Bye.